Hello once again, and let's get back into analytic trigonometry. Last time we were looking at simplifying trigonometric expressions, but now let's start to look at why we do that. The specific avenue we're going to go down is with something known as trigonometric identities. So the question begins with, what is an identity? And that is, well, if we have an expression, okay, well and good, but if we take two expressions and say they're equal or they have the same value, then we have equations, and equations can be true or they can be false. For instance, the equation 5 plus 6 times 12 minus 1 equals 121 is always true. That is an identity. Of course, you can also have equations that are never true. For instance, 12 minus 6 equals 0 is never true. There's a fancy word for that. We call those contradictions. Not that we need to worry about that now. But we do need to worry about identities. And we will need to worry about also later conditionally true equations, things that are sometimes true and sometimes not. An example of that would be this equation right here, 4x minus 17, that's an expression, 3x plus 5 is an expression, and those two expressions are equal only when x is equal to 22. So that's conditionally true. And we will concern ourselves in the next couple of weeks how to solve conditionally true trigonometric equations. For now, though, let's just worry about identities, things that are always true. How do we show something is an identity, and how do we show something is not an identity? So for starters, it's actually easier to show something is not an identity than it might be to show that something is an identity. If you want to show something is not always true, all you have to do is find one time when it doesn't work. Right, this equation right here, 2 sine x plus 3 cosine x equals 2. That can be true, but it won't always be true. In fact, if you take x to be 0, then you've got 2 sine of 0, that's 0. 3 cosine of 0, that's 3, and 3 is not equal to 2. So this equation is not always true because of our counterexample from x equals 0. So if you ever need or want to show that an equation is not an identity, all you have to do is find one exception. Of course, finding that exception might be difficult, but that's all it requires. Conversely, however, if you want to show that something is an identity, then finding that it works, finding that the equation is true for any number of values you try, that is not enough. Because the question still remains, well, what if there's something you haven't tried for which the equation is not true? More on that later. Here's an example. Here's what I want us to start looking at here. Is the equation cosine to the fourth of theta minus sine to the fourth of theta, is that equal to cosine squared theta minus sine squared theta? And it's actually going to be the case that this is something very similar to what we looked at in the last class. But at first glance, just looking at it as is, maybe our intuition is going to tell us there is no way this can always be true. I take cosine, that's some number, I raise it to the fourth power. I take some number for sine, raise that to the fourth power. There's no way that that difference is always going to be equal to the difference I get from cosine squared and sine squared. So thinking in our minds that this is not an identity, the first step we're going to try and do is try and find an exception. So we try x equals 0 again. That did us pretty well last time. But actually I get each side equaling 1. And that's because cosine is 1, sine is 0. So I raise that to the appropriate power. I'm going to have 1 on both sides. Okay, maybe we picked a bad one. Maybe we'll try pi over 4. And this is actually a bad example as well, because, that's a typo, because, well, cosine of pi over 4 and sine of pi over 4 are equal. And so if I raise them to the fourth power, I still have two equal things. That subtracts out to be 0. If I square each of them, I have two equal things. That should also be 0. See? 0. What typo? So, even then, though, maybe we just picked a bad place. Maybe it's still not an identity. We just keep trying these nice values for which it work. All right, well, let's try something weird. Let's try 16 degrees. That's not anything nice. We have to bust out a calculator for it. And we get, for 16 degrees, I get for cosine of the fourth, about that number right there. I subtract away the number for sine of the fourth, and I get about 0.848, with some rounding error, of course, but that's more or less what I get. But that's also more or less what I get for cosine squared and sine squared. Right? The difference is actually just a matter of rounding error. They are equal to any number of digits we choose to round off to. So maybe this is an identity. Right? We've got 3 times where it ended up working. That's not enough to convince me, at least, or anyone that that's always going to be true, but we now have some compelling evidence to show it. Right? Testing values, if you show it doesn't work, that means you don't have an identity. But the more values you test, and the more times it is equal, the more times it is true, that's very compelling that it is an identity. But it's not enough. It's still not enough to show it's an identity. Right? Just because it works for every value we try, there might still be something beyond the horizon that we haven't tried yet that actually shows the equation's false. Or perhaps more anecdotally, put another way, I tried and tried and tried and I couldn't disprove it, is not convincing evidence to show why something has to be true. Just because you didn't find the exception doesn't mean it doesn't exist. So we have to work more generally. So to show that our guy right here, this equation, is identically true, we can't just test points. We have to do something else. And here's what we're going to do. And here's pretty much what we're always going to do. We're going to take one side, we're going to take one expression from one side, and do something to that expression, and turn it into the expression on the other side. Because if we can do that, never changing the value along the way, we have shown that each are equal expressions. So here's what I'm going to do. I'm going to start with the left-hand side, which was the cosine of the fourth minus sine to the fourth of theta. That, again, is a perfect square minus a perfect square, a difference of perfect squares. I have a factoring technique I can use for that. So that leaves me with cosine squared minus sine squared times cosine squared plus sine squared. The second factor here is actually 1, right? That's the Pythagorean identity. So that leaves me just with cosine squared of theta minus sine squared of theta. But hey, that was the right-hand side. So we've actually shown that this thing is always equal to that thing. We have shown it's identically true. And that's how we do it. That's what we do. We take one side and turn it into the other. And that's going to be how we're going to do it for all the identities that we'll look at for pretty much this entire unit. We'll look in the next video into various techniques and tips and tricks to kind of improve the way we go about things. But at the end of the day, it's always going to be exactly that. One side, other side. So I have a question for you, and we'll pick up from there on the next video. Which of the following statements are always true? Right? Recognizing that an identity is always true. So if an equation is an identity, then the equation will be satisfied for any values we try. That's one statement. Another statement, if an equation is satisfied for every value we try, then it is an identity. Another statement, if an equation is not an identity, then it will never be satisfied for any values we try. And lastly, if an equation has no variables in it, then it's guaranteed to be an identity. So ponder on that, tell me which one you think it is, and we will pick up from there in the next video. Have a good one.